is a possible strategy, it's a logically possible strategy to defend the common cause principle, namely to say, in view of seeing a common cause incomplete probability space, not that the common cause principle is not true, but that your theory is just too meager. It's a possible strategy to say, in view of a theory which doesn't give you a common cause explanation of a correlation, which it should on the basis of the common cause principle, that the theory is just not rich enough. It doesn't have enough elements to be able to give an explanation in terms of common causes. And if you had a larger theory, then you would be able to explain the common cause principle and thereby to defend the common cause principle. And this proposition shows that indeed this is a possible strategy quite generally. It is always possible to say, logically speaking, that a theory is just too small, too meager. Every theory can be extended in such a way that the extension will be purely non-atomic, and in that space, common causes exist for every correlation. Okay? So purely non-atomic spaces are important because they are just extremely rich. Clearly, a purely non-atomic probability space has to have a continuum number of random events. It's clear from the definition. The cardinality of a purely non-atomic probability space, the cardinality of the Boolean algebra, is at least as large as the continuum. Okay. Further twist on this notion, the notion of common cause completeness and common cause completability can be strengthened. One can define, namely, the type of the common cause in terms of the values of the probabilities which are indicated here. You might want to say, okay, there are different common causes possibly for a correlation, and a particular one can be characterized by fixing these conditional probabilities and the probability of 2. And then you can show that for a correlation typically, in principle, there's a continuum number of these numbers which you can fix and which is allowed in principle for the common cause to satisfy. And then you can call a probability space strongly common cause complete. It contains a common cause of every possible type of every correlation. Clearly a very strong notion. And it's not clear whether this notion is self-contradictory or whether it is maintainable. Questions which are open at this point. Do strongly common cause complete probability spaces exist? And if yes, are probability spaces strongly common cause completable in the sense in which I described? My suspicion is that the purely non-atomic probability spaces are strongly common cause complete. That is to say, they have so many events and probabilities are so fine-tuned that every type of common cause there can be found. But these are open and they are completely well defined. There's a proposition here which I would like to state, namely, it could be proved that every classical probability space is strongly common cause extendable with respect to any finite set of correlations. So if you have a probability space which is common cause incomplete, you can extend it in such a way that you can extend it in the following way. You fix the type of the common cause, and I can give you an extension which contains a common cause of the prescribed type. Okay? This is possible for any finite set of correlations, and I think it's reasonable to conjecture that this proposition holds for a countable infinite set of correlations, but this has not been proved yet. I think it's just a technical raffinery which would be needed here, and I think that should be provable. Okay, so much about the common cause problem in the classical context. This is the origin of the problem of the common cause investigation in the non-classical, non-commutative context. Because of course you can replace the notion of common cause, but you can design the notion of common cause in a non-classical probability space. How? Well, you replace the classical probability measure space with a non-classical one, typically by the von Neumann lattice of projections, as replacing the Boolean algebra and taking a normal state. And then you can define the correlation between compatible elements, and then you also can design the analog of the notion of common cause in a non-classical probability space just by taking over Reichenbach's definition without essentially any modification. Namely, if you assume that the common cause, or you require that the common cause of a correlation is supposed to be such that it is compatible with both A and B, which means that they are from the same distributive sublattice, and it satisfies the screening of and the statistical relevance conditions. To recognize that these are just screening of conditions taken over from Reichenbach's definition, and these are the statistical relevance conditions. So this is the definition of common cause in a non-commutative probability space. It is a conservative definition in the sense that C is assumed required to be compatible with both A and B. I come later to the question whether it makes sense to weaken this condition by allowing C to be non-commutative with A and B. And then the notion of notions and problems which have been defined in the classical context can be defined without any modification in this non-classical context, namely the type of the common cause, the logically independent sublattices, the causal incompleteness, completeness, completability, extendability, the strong common cause completability, pure non-atomicity, everything which has been defined in the classical context can be defined without any problem in this non-classical context, and the same type of questions and problems arise, and many are open. Here are some results which have been known in connection with this issue. There is a proposition which is due essentially to Ichiro. We improved upon it a little bit, not much, just a little bit. The proposition is that if you have an atomless sigma-complete orthomodular lattice, and phi is a sigma-additive faithful probability measure on the lattice, then that space is purely non-atomic. And if it is non-atomic, then it is common cause complete. And if it has two or more phi atoms, then it is not common cause complete. So quite essentially, the point is that essentially the same is true as what is true for the classical case. Okay. All right. There is also a proposition which is in progress. We are just writing a paper on this, which is also the analog of the classical proposition. Remember, the classical proposition was that every probability space is extendable, embeddable into a purely non-atomic one. And this is also true in the non-classical case. And we think we have shown this, we are just writing up the paper, so this is in progress. So every non-classical probability space can be embedded into a purely non-classical one, which means also that the argument which I specified as a defense, possible defense of the principle of common cause in the classical context can be extended, is valid, can be extended to the non-classical case, is valid for the non-classical case as well. Because purely non-atomic ones are common cause complete. There are problems here which are open. The question is, one question which is open is whether every common cause incomplete non-classical probability space is strongly common cause completable. I suggest that the answer is yes. And also, weaker question, whether every common cause in complete non-classical probability space is strongly common cause extendable. This is different than completability strongly, and I think the answer to that question is yes, too, but this has not been proved. These are open questions. Now I'm approaching the issue of the status of the common cause principle in quantum field theory by relating the general statement by Ichiro and ourselves about the non-atomic situation. We note that the type 2 and type 3 von Neumann algebras are non-atomic as lattices. The projection lattices of type 2 and type 3 von Neumann algebras are non-atomic. And if you have a faithful measure on them, which are normal, then the probability space, which is defined by this probability, by this faithful normal state, are common cause complete. But there's particular cases of the general proposition. And the significance of this proposition is that, as we have seen in connection with the Bell correlation, quantum field theory does predict correlations between projections that are localized in algebras which are pertaining to space-like separated space-time agents. And since space-like separated space-time agents are causally independent, if you want to explain these correlations in the spirit of the common cause principle, they should be explained and explainable, and the only way to explain them is to explain them in terms of some common cause. And this proposition indicates that this should be possible because there's a common cause of this type of correlation. Because the local algebras in quantum field theory, as we have seen, are type 3, and so there are common causes of this correlation. So are we happy about this, or are we not happy? Well, we are a little bit happy because this opens up the possibility of the causal completeness of quantum field theory. On the other hand, we shouldn't be completely happy at this point because if you remember, algebraic quantum field theory is a local quantum field theory. So you would only want to say that it explains the correlation between space-like separated quantities if the common cause which is required for the explanation is localized in a peculiar way. Okay, so the common causes should be not just any projections which we know that such a projection exists, but they should exist in a particular local algebra. Okay, so where should they be localized in the first place? Well, obviously, they should be localized somehow in such a way that they intuitively respectable in the sense of being capable of affecting the correlated entities causally. Now, there are 3 possible regions of locality which you can think of, and here they are defined formally. But I think I should better draw a picture which makes it more understandable what's going on here in terms of regions. Suppose you have 2 space-like separated double cones. This will be the typical situation. These will be the local algebras which contain correlated projections. And you draw the backward-like cones. Oops, it's not that nice, but it's all right. So where would you like the projection to be? Well, ideally, you would like to have the projection to be localized where somewhere where Where would you like to be? Where would you like it to be localized? Well, in the intersection of the backward light cones of the two regions. Where are they? So that's the backward light cone of this one. That's the backward light cone of this one. So you want it to be somewhere here. Right? But you can also define it to be somewhere here. That's a possible region as well. And a possible region also to say that they are somehow in the union of the two backward light cones. So the whole region from here, they're taken out, the two regions taken out of it. Okay? So there are three possible localizability regions. They are defined on the slides, okay, formally. And they have different causality properties. As I say here, this is the strong path, the intersection of all the backward light cones of all the points. If there is something here, then from that point you can reach any point here and there by a time-like curve. Okay? And if you're somewhere here, you can reach at least one point. If you're in the union of the backward light cones, then every point in that can reach at least one point in either here or there. If you're in the intersection of the backward light cones, then it is the case that from any point from that, you can reach one point in both that and here. These are the differences. Okay? Clearly, they are different in their causal behavior, different in their causal strength, so to say. So these are three possible localizability regions for the common cause. And the question, and ideally what you would like to have is to have a common cause which has the feature that it can reach one point here and one point there. That is to say, the intersection of the backward light cones. That's what you would like, because that's the intuitively attractive position, namely there's a correlation here. There's supposed to be something there which should be able to reach both that one and that one. Now, the question is then what the situation is about the localizability. So here's the definition of local common cause. You say that the field theory, the local field theory, satisfies the weak common cause principle, respectively the common cause principle and the strong common cause principle, if it is the situation that for any two regions, V1 and V2, if there is a correlation between the elements A and B that belongs to V, AV1 and AV2, which are space-like, there will be a common cause in an algebra which is located in the weak past, strong past, weak past, common past, and strong past of the two regions. If this is the case, then you say the system satisfies the weak common cause principle, the common cause principle without any adjective, and the strong common cause principle. Okay. That's a crucial definition. That's the heart of the whole matter. Again, you would say that quantum field theory satisfies the common cause principle if it is capable of giving an explanation of this space-like correlation in terms of properly localized common causes, where properly localized means it's an intersection of the backward light cones, or you say that it weakly satisfies the principle if there is a common cause localized somewhere in the union of the backward light cones of the two regions, and the strong common cause principle if it is localized in the union of all the intersection of the backward light cones of all the points. Now, the following is true. If you have a quantum field theory which has the standard features, then the local net satisfies the local primitive causality. And if the net satisfies the local primitive causality condition, which I'm going to define on the next slide, then the field theory is weakly causally complete. in the sense of being able to provide an explanation in terms of weakly localized common causes. It's not strongly causally complete, and it's not known if it is causally complete without any adjective, stronger than weak, weaker than strong. So we don't know if properly localized, properly meaning in the intersection the common causes exist. We know that they cannot exist here in the strong common cause simply because, if you remember, Bell's inequality is violated for complementary wedges, and for wedges, the strong common past is empty, so there's simply no room for any common cause to be localized in that region, so it's violated. But unbounded regions are tricky anyway. What one would really like to have is bounded regions, essentially double chromes, and for double chromes, this is not anything. And what we know, the only thing we know, is that weak causal completeness holds for space-like separated double chromes. The philosophical conclusion, if I may call it a philosophical conclusion, is that these space-like correlations, although, as I have argued, are very endemic in quantum field theory, they are everywhere, still do not provide confirming evidence in favor of the rejection of the common cause principle. They cannot be regarded at this point as disconfirming evidence for the common cause principle, not even if the common causes are required to be local. But it's not known whether properly localized common causes do exist. Here's the definition of local primitive causality. Remember when I listed the axioms for algebraic quantum field theory, I mentioned in red local primitive causality. It's not part of the standard definition of the standard axioms. There are quantum field theories which do not satisfy it, but typically it is satisfied. This is the condition, which is an expression of the hyperbolic character of the time evolution. But the formal expression of it is that the algebra, which is associated to the causal completion of a region V, is equal to the algebra which is associated with the region. So the way to imagine this is that if you have, say, a region like this, then the algebra which is associated with this one is the same as the one which is associated with the causal completion of it, which would be a double cone. So this is the double cone. This is X, this is Y, and this is the algebra which is associated with the double cone. And the local primitive causality condition says that the algebra AV is supposed to be equal to the algebra A associated with the double cone. Okay? So everything that that happens here determines, or everything which is observable here determines what can be observed in the causally completed region. Okay? This is strong enough, sufficient enough to define what's going on in a slightly, possibly slightly larger region. And that's the content of the local primitive causality condition. Here's an equivalent formulation of it, of what it means for a region to be causally complete. Okay, so if this condition holds, then big common cause principle can be shown to hold. Now, the problem whether the common cause principle holds without the adjective weak has been around for quite a while. And there was an idea, and then it's open. And there was an idea of why not trying to see what the status of the principle is in lattice quantum field theory, discrete quantum field theory, where computation is a bit more accessible because it's more more explicitly, I mean, the algebras there, as we will see in a second, are finite dimensional. They're more amenable for computation. So two physicists, one of the students of mine, had embarked on investigating the status of this homunculus principle in lattice quantum field theory. So let me just tell you what the situation is, what they have found. First, a few words about lattice quantum field theory in two dimensions. The discrete 1 plus 1 dimensional Minkowski space-time is just a subset of the discrete points of the 1 plus 1 dimensional standard Minkowski space with time coordinates and space coordinates which have this form. And the time coordinate must be of this form where n is an integer. So if it is a half integer, the time coordinate is a half integer, then the space coordinate must be an integer. And if the time coordinate is an integer, then the space coordinate must be a half integer. That's the idea. You should imagine a lattice. Imagine the two-dimensional Minkowski space-time, and you imagine a lattice on it, a standard lattice, which you somehow rotate by 45 degrees. That's what the discrete version of it is. Okay, with the space-time structure which is inherited from the one-dimensional Minkowski space-time. There will be a picture in a second, and you will see what's going on more precisely. You can define double cones in that discrete space-time. Namely, you do the standard double cones and intersect it with the discrete points. And then you also can define minimal double cones, which it doesn't make sense to talk about points which have minimal distance in that space-time. And here's an example of what the minimal double cones in the discrete space-time would be. If you have 2 points, x and y, they have this form of the coordinates. And if n y is mx plus 1, then y is the future light cone of x, the unit time distance. And then the double cone determined by these 2 points, x and y, have 2 points. Okay. And this is a minimal double cone because the distance between the elements is minimal. Here's the picture perhaps that shows what's going on. So here's space, here's time. These are the points. As I said, it's just a rotated lattice in the two-dimensional plane. And here are the points which are parts of the discrete space-time. This is 1 over half, this is 1 over half, 1 over 2, this is 1 half, 1 half. So a point which has this point has a half integer time coordinate and an integer space coordinate. This again half integer time coordinate and integer space coordinate and all the rest. And if you have 2 points here, x and y, this is the double cone. The red dots signify the double cone defined by x and y. Of course, y is the future light cone of x. You take the backward light cone, forward light cone, the intersection of it is these 2 points. And these are the minimal double cones. Very straightforward. And if you have the minimal double cones, then you can associate finite dimensional algebras with the double cones in such a way that you obtain a discretized version of the net, which has all the features which correspond to the features, to the axioms of the full-fledged quantum field theory, namely isotony holds for the net, the closure of the double cone algebras defines the quasi-local algebra. It will be a specific quasi-local algebra, uniform hyperfinite. It has an increasing set, an increasing sequence of finite dimensional full matrix algebras. Einstein locality, local commutativity holds, and there is a representation of the unit space and time translations, and local primitive causality also holds for the net. I'm not telling you how this can be done. This can be done. It's standard how you associate matrix algebra to the minimal double closed so that these features are satisfied. The point is just that you have a discretized version of the algebraic quantum field theory in 1 plus 1 dimension. And of course, in that set, the space-like correlation, the notion of common cause, the weak and strong locality of the common cause, all make sense, just like they make sense in the full-fledged version of quantum field theory. And then you can define the compliance of the discrete quantum field theory with the common cause principle, respectively in the weak and strong senses. So you can essentially, what you can do is you can translate the situation and the concept, the notions, in the full-fledged quantum field theory into the two-dimensional, 1 plus 1 dimensional discrete quantum theory. And you can ask the same questions with the hope of being able to show something which you were not able to show in the general case. Okay? So the question is what the status of the common cause principle is then in this discrete quantum field theory. This is just to recall the notion of localizability of the common cause. I'm skipping this because I've explained. So does the weak and strong and without adjective common cause principles hold in that theory? That's the question. And here's a proposition which is relatively recent in Foundations of Physics 2010. The weak common cause principle fails in discrete quantum field theory. Okay, so remember that the weak common cause principle did hold in the general case. They have shown that it fails in the discrete version. And as a consequence, the common cause principle also fails, and the strong common cause principle also fails because the weak is really weak. Is this surprising? To some extent, this is surprising because, as I said, the standard quantum field theory does satisfy the weak common cause principle. Why should the discrete not do so? You would not expect a causally different behavior in the discrete case. Remember, the intuition was, the original motivation for such an investigation was the hope that in the discrete case we have a better handle on the algebras and we might be able to say more, prove more than we could in the general case. And this intuition proves to be incorrect in some sense. On the other hand, I don't think this is very surprising in view of some of the results which I presented you. Namely, the local algebras in lattice quantum field theory are isomorphic to full matrix algebras, as I said. And therefore, the quantum probability theory, which is defined by such algebras, are measured theoretically not purely non-atomic. And the general results on common cause completeness in non-classical probability spaces show that measured theoretic non-atomicity is essentially equivalent to common cause completeness. So what you would expect is that certain correlations in that discrete version do not have a common cause within these non-atomic structures at all, irrespective of localizability. Remember that in the general case, there were common causes as a consequence of the purely non-atomic feature of the probability theory, but we just were not able to localize them. In this discrete case, there are no such common causes at all, irrespective of localizability or not. And indeed, if you have a look at the proof of that proposition, then you see that the proof is not the failure of the weak common cause principle is not that there are common causes which cannot be weakly localized. The situation is that there are no common causes at all whatsoever. Okay? Locality is in that sense irrelevant. So, what are the options in view of this failure of weak common cause principle in discrete field theory? Well, you can say that one should disregard the failure as physically irrelevant because it's just a result of the lattice model's peculiar feature that if it's too coarse, it's measured theoretically discrete. And then you might want to say that in the continuum limit, this artifact disappears. Now, these are very new results. I don't know what to think about them. Really, it would be interesting to see if there is some evidence for this hope in the second point here. I'm not sure, but certainly I don't see any evidence for this. Another option is that you might want to think about the notion of common cause again, and you might want to weaken it in such a way, in a disciplined way, that the measure theoretic discreteness of the quantum probability space is no longer an obstacle to obtain common causes. And this is possible. How would you weaken the notion of common cause? Well, there are two possible ways. One is to replace the common cause by a common cause system, and the other way is to abandon the requirement that the common cause events are compatible with the correlated events, that they are from the same distributive sublattice. I mentioned this to you in the beginning, emphasized that it is part of the definition that they are compatible with A and B, the common causes, and you might want to abandon that requirement. So these are two possible ways of, possibly not the only possible ways, but two possible ways of weakening the notion. Now, option one, what can be done leads to new definitions and problems, of which many are open, namely going to the common cause system rather than the common cause. But it doesn't have. In the paper which I referred to previously in connection with this proposition, it is shown that the lattice does not allow common cause systems either. So there is no system due to the discreteness of the lattice. The other option does have, namely if you weaken the notion of common cause by abandoning the requirement that it's compatible with the correlation, then something can be done. I skipped the common cause system issue, which will not fit here. It's interesting in its own right, but I moved to the non-commuting common cause system definition. So here is the definition, which is a definition of common cause system, and which also abandons the idea, the requirement, that the common causes in the system should commute with the elements which are correlated. So suppose you have a partition in a quantum probability space, and this partition is called a non-commuting, or possibly non-commuting, Reichenbach common cause system for the compatible events. If for all elements in the partition we have the following: first of all, that they screen off the correlation, and second, that they have they satisfy an analog of the statistical relevance summation. But now, instead of the classical conditionalization, you have the non-classical conditionalization, the Lüder's rule. Okay? Since CK is now not assumed to commute with A and B, you conditionalize with respect to the quantum conditionalizing rule. That's the Lüder's rule. Okay? So you have here a substantial weakening of the notion of the common cause. First, because we allow for common cause system, many elements in the partition, not just C and C orthogonal, but a partition which can have a larger cardinality. And you also replace the classical conditionalization with the quantum conditionalization. And then you call this a non-commuting Reichenbachian common cause system. I would like to mention that you also might want to drop the second condition, weaken the notion of common cause even further by dropping this condition completely. If that's done, then you call this common cause system a non-Reichenbachian common cause system. And with obvious specification of locality, you can then define the non-commutative weak common cause system principle, the non-commutative common cause system principle, and the non-commutative strong common cause system principle, and you can ask the same questions as before for this new notion of common cause system. And then the problem is what the status of these common cause systems principles are in quantum field theory. This is very new, hardly anything has been done in connection with this. It is essentially open. The only known result is in a very recent paper which has been submitted. I don't know if it has been available in from the preprint, but the claim is that the non-commutative common cause principle holds in lattice quantum field theory. That is to say, allowing for the non-commutativity of the common cause system, the elements in the partition, compensates for the discreteness of the lattice. So here now you can show that there are weakly localized common cause systems for the correlations, discrete 1 plus 1 quantum field theory. Nothing is known in higher dimension, and nothing is known for the not weak common cause system. So again, nothing is known about the status of the common cause principle, not in the weak sense, in the proper sense. Again, proper meaning that the common causes are localized in the intersection, where you want them to be. Nothing is known about this problem. It's been around for 15 to 20 years, I don't know. First time it was formulated, I believe, it was in my paper 1998 in Foundations of Physics. And the problem is open. Now, given this openness of the problem, you start speculating. Why don't we know what the situation is? And here's a logical possibility, which is an intriguing possibility. Namely, you recognize that quantum field theory is specified by axioms. And the causal completeness is a property of quantum field theory that holds or doesn't hold as a consequence of the axioms. But it is a logically possible option that the axioms are not strong enough to determine the question. So the axioms are just too weak to give an answer to the question whether properly localized quantum causes exist or not. Now, this is a logical possibility, and it's an intriguing one. If you formulate this, if this idea happens to you, as it has happened to me anyway, then you might want to conjecture that indeed this is the case, that this is the claim of the causal independence in that sense is an independent claim. It's not provable, but its negation is not provable either. Now, to prove this conjecture, of course, how do you prove independence of a statement of the axioms? Well, by providing a model in which the statement is true and providing a model of the axioms in which the statement is false. Now, to do that seems almost beyond hope, at least for me. But this is what could be in principle done, and it seems to be very difficult. I think what one should do is perhaps to have a look at the existing models of the axioms and have a look at, in those particular models, what the situation is. And this has not been done yet. So there's a lot to be done still. If you're interested, I hope I excited you a little bit about this. And here's a summary of what I've said today. First, the common cause principle states that probabilistic correlations have a common cause type explanation if they are not results of a direct causal link between the correlated events. That's the general principle. And since we have seen in the previous lecture, local algebraic relativistic quantum field theory predicts correlations between space-like separated observables. The causal completeness of that theory would entail, should entail, the existence in field theory properly localized common causes of such space-like correlations. And at present, it is an open problem whether such common causes exist, which are localized in the intersection of the vector-like modes of the space-like separated observables. Only common causes localized in the union of the vector-like modes are known to exist. And a very speculative idea might be undecidable on the basis of the axioms of quantum field theory. The common causes possess stronger locality properties. It would be very interesting, I think, if this turned out to be the case. And with this, I think I'm just on time, and I finish, and thank you very much for endurance and for your attention again, and see you tomorrow if you feel like. Thank you.